Let's talk about elementary matrices. Recall the three elementary row operations. Interchange two rows, multiply a row by a non-zero constant, add a multiple of one row to another row. For any elementary row operation, we can find a matrix E such that performing an elementary row operation on a matrix A is the same as multiplying A on the left by E. For example, let A be 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's perform this elementary row operation. Interchange two rows, say rows 1 and 3. We obtain 7, 8, 9, 4, 5, 6, 1, 2, 3. We can find a matrix E such that interchanging these two rows of A is the same as multiplying A by E. And that matrix E, 0, 0, 1, 0, 1, 0, 1, 0, 0. Where did I get it from? You'll see a little bit later. When we multiply A on the left by this matrix E, we get 7, 8, 9, 4, 5, 6, 1, 2, 3. That's the matrix we saw earlier. Interchanging these two rows, R1 and R3, is the same as multiplying A by E. Let A be the same matrix. Let's perform this elementary row operation. Multiply a row by a non-zero constant, say 10 times R2. We obtain 1, 2, 3, 40, 50, 60, 7, 8, 9. We can find a matrix E such that multiplying R2 by 10, row 2 by 10, is the same as multiplying A by E. And that matrix E, 1, 0, 0, 0, 10, 0, 0, 0, 1. When we multiply A on the left by this matrix E, notice what we get. 1, 2, 3, 40, 50, 60, 7, 8, 9. Multiplying the row R2 by the non-zero constant 10 is the same as multiplying A by this matrix E. Lastly, let A be the same matrix. Let's perform this elementary row operation. Adding multiple of one row to another row. Let's say 10 times row 2 added to row 1. We obtain 41, 52, 63, 4, 5, 6, 7, 8, 9. We can find a matrix E such that adding 10 times row 2 to row 1 of A is the same as multiplying A by E. And then matrix E, 1, 10, 0, 0, 1, 0, 0, 0, 1. When we multiply A on the left by E, we get the matrix we saw earlier, 41, 52, 63, 4, 5, 6, 7, 8, 9. So adding 10 times row 2 to row 1 of A is the same as multiplying A by this matrix E. How did I figure out what E should be in each case? Have you figured it out? Each of these matrices E is an elementary matrix. An elementary matrix is the matrix we obtain when we perform exactly one elementary row operation on an identity matrix. Okay, now this slide is kind of complicated, but I'm going to go through it slowly because it's important and it helps us to understand where matrix inverses come from. If an elementary row operation is performed on an m by n matrix A, the resulting matrix is EA, where E is the elementary matrix we obtain by performing the same row operation on the m by m matrix I sub m, identity matrix. Performing that operation on A, in other words, is the same as performing that operation on an identity matrix I sub m to obtain a matrix E and then multiplying A on the left side by E. I'll show you an example. Interchanging these two rows, R1 and R3, is the same thing as multiplying A by E. Where did this matrix E come from? We took the identity matrix and we performed this same elementary row operation on it. Namely, we interchanged rows 1 and 3, and then we got this. And that's how we find the matrix E that we need to multiply by A in order to obtain the matrix we would have obtained had we performed that elementary row operation on A. Same thing here. Multiplying the row R2 by the non-zero constant 10 is the same as multiplying A by this matrix E. And what is this matrix E? It's just the identity matrix that's had this same elementary row operation performed on it. Namely, the second row has been multiplied by 10. Lastly, adding 10 times row 2 to row 1 of A is the same thing as multiplying A by what? Well, let's figure it out. Here's our identity matrix. Our elementary row operation is 10 times row 2 added to row 1. So if we multiply row 2 by 10, we get 0, 10, 0. And now let's add that to row 1. Row 1's going to be 1, this is going to be a 10, and that's going to be a 0. So that's our matrix. Our matrix is E, 1, 10, 0, 0, 1, 0, 0, 0, 1. Again, that's the matrix we obtain when we perform this same elementary row operation to the identity matrix. That's the matrix we need to multiply A by. Here's why this is important. It enables us to find the inverse of an n by n matrix A. When we use elementary row operations to transform A into I, it is the equivalent of multiplying it by elementary matrices. Okay, because again, when you use Gauss-Jordan elimination to reduce A to the identity matrix, it's like multiplying A by elementary matrices over and over and over again, because we've seen that each elementary row operation corresponds to a certain elementary matrix. Okay, so you perform these elementary row operations. Here are the elementary matrices you multiply A by to get I. But notice, since this times A equals I, we know that this stuff is A inverse, because if you're multiplying it by A to get the identity matrix, it must be A inverse. This leads to a technique that we can use to find the inverse of an n by n matrix A. So write AI. So you write A on the left side, write I on the right side of your matrix. Perform elementary row operations on A to reduce it to I. Whatever you do to the left matrix, namely this one, also do to the right matrix, namely this one. When you are done, the left side will be I, and the right side will be A inverse. And again, that's because everything you've done to A, everything you've done to A is like multiplying A by an elementary matrix. So basically what you're finding is this product, E sub n minus 1, etc. Okay, so find the inverse of A equals 1, 2, 3, 2, 5, 3, 1, 0, 8. First, we set up this matrix, AI. This is our A, and this is, of course, our I. We're going to row reduce A using Gauss-Jordan elimination. So first, let's kill off this 2 over here. So we're going to multiply row 1 by negative 2 and add it to row 2. We would end up with this. Okay, so again, you multiply row 1 by negative 2, you'd end up with negative 2, negative 4, negative 6, and then negative 2, 0, 0. Let's add this to row 2. When you add this to row 2, this is what row 2 becomes. So negative 2 plus 2 is 0, negative 4 plus 5 is 1, negative 6 plus 3 is negative 3, negative 2 plus 0 is negative 2, 0 plus 1 is 1, and 0 plus 0 is 0. Okay, next, let's add negative row 1 to row 3, and we're going to use that to kill off this one over here. When we do that, okay, here's what the opposite of row 1 looks like. When we add this to row 3, here's what the new row 3 is going to look like. Okay, negative 1 plus 1 is 0, etc. So we just end up with 0, negative 2, 5, negative 1, 0, 1 as the bottom row, the new row 3. Now what do? Let's add twice row 2 to row 3. Again, what we're trying to do is kill off this negative 2 here. So we'll add twice row 2 to row 3. Here's twice row 2. And when we add that to row 3, notice what we end up with. 0 plus 0 is 0, 2 plus negative 2 is 0, etc. We just end up with this matrix here. Now, let's look at the opposite of row 3. Let's multiply row 3 by negative 1. We're just going to end up with this for our new row 3. Let's add 3 times row 3 to row 2. So we're going to use this to kill off this negative 3 here. Multiply row 3 by 3. This is what we end up with, multiplying row 3 by 3. Add it to row 2. 0 plus, you go ahead and do that, and this is what you end up with. So 0 plus 0 is going to be 0. 0 plus 1 is 1, etc. And this is going to end up being your new row 2. Now let's add negative row 3 to row 1. Again, we're going to try to kill off this 3 up here. Here's what negative row 3 looks like, the opposite of row 3. 0, 0, negative 3, etc. Okay, so we add that. We add this to row 1. And the new row 1 becomes, well, 0 plus 1 is 1, 0 plus 2 is 2, negative 3 plus 3 is 0. We end up with this as our new row 1. Now, lastly, let's kill off this 2 by adding negative 2 times row 2 to row 1. So here's negative 2 times row 2. When we add that to row 1, this is what our new row 1 looks like. And we're done, folks. Look at this. This is what we end up with. This is our identity matrix, and so this must be A inverse. So the answer is going to be A inverse equals this. Phew, that took a while. Since every elementary row operation can be reversed, every elementary matrix has an inverse. There is some elementary row operation that turns E back into I. So there is an elementary matrix F such that Fe equals I. What if A is an n by n matrix and its reduced row echelon form is not I? Then A is not invertible. Can't happen. Let's find an elementary matrix E such that E times 1, 2, 3, 4 equals 1, 2, 4, 6. Okay, notice E corresponds to this elementary row operation. Add R1 to R2. Okay, so let's just go ahead. Yeah, if you add row 1 to row 2, add row 1 to row 2, you just end up with this matrix here. So E corresponds to this elementary row operation. All we have to do is do that to the identity matrix. Add row 1 to row 2. And notice what we get. Our elementary matrix E is 1, 0, 1, 1.